Hello, Chem51 students. Today I will be going over the discussion quiz for chapter 1. So starting with number 1, the question asks, what is the correct Lewis dot structure? So moving from left to right, if we first look at that first carbon atom, it has 4 bonds to it, implying it has 8 electrons, and this follows the octet rule. If you can recall, all atoms need to have at least 4 bonds or a total of 8 electrons onto it to follow the octet rule, other than hydrogen. Moving to the next atom, if we look at that oxygen, this has 2 bonds to it, implying it only has 4 electrons. This needs an additional 4 electrons to follow the octet rule. So that structure is incorrect. Moving to structure number 2, if we look at the first carbon, this has 4 bonds to it, so it follows the octet rule. The next carbon has 2 single bonds right there, and a double bond, which is a total of 4 bonds, following the octet rule as well. This oxygen has those 2 same double bond, along with 4 electrons, which follows the octet rule. If we look at this oxygen down here, this one only has the 2 single bonds on both sides, so it's also missing the additional 4 electrons. So that structure is also incorrect. For structure number 3, if we look at the first carbon, this has 2 single bonds and a double bond right there, which is a total of 4 bonds, 8 electrons, follows the octet rule. If you look at this oxygen right here, this one has a double bond along with 2 lone pairs, which is a total of 8 electrons as well. That follows the octet rule. This oxygen down here has 2 single bonds, and that's it. So this is also missing the additional 4 electrons to make it a total of an octet. So this structure is also incorrect. For the next structure, we have to look at the first carbon. This has 4 single bonds to it, a total of 8 electrons following the octet rule. This oxygen right here has 2 singles and 2 lone pairs, which is a total of 8 electrons as well. That follows the octet rule. This carbon right here has 4 single bonds to it. This one also follows the octet rule. So this is the correct structure out of the 4. Okay, moving on to question number 2. The question asks, what is the ground state electron configuration for nitrogen? So to know this, you need to know the periodic table or have an idea of where nitrogen sits on the periodic table. I drew a condensed version down on here. So starting with hydrogen in the top left, hydrogen is going to be 1s1. Moving to helium is going to be 1s2. Lithium is going to be 2s1. Beryllium is going to be 2s2. Boron is going to be 2p1. Carbon is going to be 2p2, and nitrogen is going to be 2p3. So the electron configuration should be 1s2 fully filled, 2s2 fully filled, and 2p3 partially filled. All right, for question number 3, they're asking how many constitutional isomers there are for C4H9Br. The easiest way to do this is actually just draw them out. So using carbon as a backbone, I usually like to start by drawing the linear chain first and then branch off of that, because that kind of gives you all your options. So to see this, I drew 4 carbons in a line. You know that each carbon needs to follow the octet rule. We have 9 hydrogens to spare right now. So the first 3 will go on this first carbon to follow that octet rule. Next 2, this would be 5 hydrogen total onto the second guy. Another 2, that would be 7 hydrogens total on the third one. And now we're missing 2 extra hydrogens as well. So those 2, that's 9 hydrogens total. So our last bond is going to be to bromine. One key thing, we need to draw on our electrons to follow that octet rule. So one key thing about constitutional isomers are they have different connectivity. So when you have a structure formula like this, one easy thing to do is just to flip these right here. So if you flip those 2 structures around, they would look almost identical. and it'll look like that. So the next thing I would do is then try to branch off of it. So we draw 3 carbons long. We can branch one off right there. So now following the octet rule again, this carbon needs 3. That'd be 3 hydrogens used up. This would need another 3. That'd be 6 hydrogens used up, and this would be another 3, which would be 9 hydrogens. Our last bond would be to the middle carbon, which would be the bromine. I'm drawing our lone pairs again to fill that octet rule. Of course, another, like I said before, the easy switch is just switching this bromine with a hydrogen. This will then give you a very similar structure. So these are the 4 structures you can get from this formula, condensed formula. If you move this bromine onto any one of these other carbons, it'd actually be the exact same. If you move this bromine, onto any one of these other carbons, it'd be the same structure as you already have. And then if you move it back to the middle, that's just going back to this way. Additionally, the same thing is the case for above. So these are the 4 constitutional isomers. Okay, so next we're going to talk about question number 4. What is electron geometry on the indicated atom? For this, you want to think about how many things are attached to each atom. By thing, I include single bonds as a single thing, of course, double bonds as a single thing, triple bonds as a single thing, and lone pairs as also a single thing. So for the first structure, this is going to be carbon dioxide. We're looking at this carbon in the middle. It has 2 things attached, so this would be 2 sets of double bonds. So that's going to be sp, which is going to be linear. Next, I'm going to look at the second structure, which is ammonium. We're going to look at this middle nitrogen. So this one has 4 things attached to it. So this is going to be sp3, and it's tetrahedral. For number 3, we're going to be looking at this middle carbon, and this is formaldehyde. This one has 3 things attached to it, 2 single bonds, and this double bond is the third one. This is going to be sp2, and it's going to be trigonal planar. The next structure is going to be water, and we're looking at this oxygen in the middle. This thing has 4 things attached to it, 4 things, 2 sets of lone pairs, and 2 single bonds, a total of 4 things. And this is going to be sp3 and tetrahedral. One thing I would like to point out, because I always get this question, is that there is a difference between electron geometry and molecular geometry. A lot of people come up to me and say, well, I was taught that water is bent. That is true. That is a molecular geometry of the atom. That is not the electron geometry. All right, so next we're going to answer question number 5. The question is asking, turn this skeletal structure or this condensed formula into a skeletal structure. So just know that whenever you ever see anything in parentheses, that means that those are all going to be attached. Everything in these parentheses is going to be attached to whatever atom is following next. Okay, and then just read left to right, and just know that if a letter is by, or one atom is by another, these have to be attached. Okay, so I always start with the ones in parentheses. We know we're starting with that carbon right there, and it has to have 3 groups attached to it, which are 3 methyl groups. Each one has 3 hydrogens. Oh, shoot. Okay, and then so we took care of this section right here. We're then gonna have an oxygen, and then a hydrogen. To follow the everything follows the octet rule, we have to draw on our lone pairs on the oxygen. Now I know they might look different on your answer key. So this is the actual skeletal structure that we're trying to draw. Is the way that as chemists draw, we draw carbons as like that. So pretty much at every point, just know that it's a carbon and that each carbon follows the octet rule. If it's not showing you everything, it's showing you, if it's not showing you all the atoms, just know that there's enough hydrogens to fill the octet rule. All right, moving forward, on this last part, the question asks, okay, so now moving to part B of the quiz. The question asks, draw the Lewis dot structure of ethylene. So to do this with C2H4, so we know we only have 2 carbons, okay, and each carbon has 4 valence electrons. And this now needs to have only 2 hydrogens, or 4 hydrogens, excuse me. So let's draw 1, 2, 3, 4. And I always just like to draw them kind of far and then match them. So we know that 2 electrons make a bond. If we connect those 2 together, if we connect those 2 together, those 2 together, those 2 together. Right. Now we need to make sure we have those bonds connected, but now to finish the octet rule, each carbon needs an additional one, so we need to make an additional bond to that. So to draw this out, we're going to draw it like this. Hydrogen, 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 hydrogen. Okay. So for part B, now it's telling us label the hybridization. And then part C says describe the bond angles on the carbon. So the hybridization, we're going to look at the carbons. So again, we're going to think about how many things are attached. If we look at that carbon, we have technically 1, 2, 3 things attached, and which is going to be sp2. And then this carbon right here is going to be exactly the same sp2 as well, with 1, 2, 3 things attached. And then it says describe the bond angles. Like I said, for everything they want to be furthest apart. If you remember the hybridization, or you can figure out the hybridization and you can remember the bond angles are always the same. So for sp2 hybridized atoms, the bond angle is 120 degrees to be farthest apart, and that's going to be trigonal planar. So to answer the last question of the discussion quiz, we have to take into consideration what kind of hybridized orbitals we're using to make our bonds. So for in this case, each one of the carbons is an sp2 hybridized orbital, in which that it implies that each orbital consists of 1 s orbital and 2 p orbitals. However, this also means that each carbon has an open p orbital unoccupied. So to draw the carbon-carbon single bond, this is going to persist of a sp2 orbital, hybridized orbital, that overlaps head-on. I don't know why one side's bigger. That makes up the carbon-carbon sigma bond. Next, you're going to have these same sp2 hybridized orbitals to overlap head-on with the s orbitals of the hydrogen. So to draw that, again, we're going to draw another. I'll make the hydrogen s orbital that color, and then one more. And then for this other carbon, you're going to have another with the two s orbitals from the hydrogens. So those make up all the sigma bonds. However, ethylene has a double bond. So what makes up the other pi bond is going to be these two unoccupied orbitals on p orbitals on carbon. So to draw those, we kind of just draw them up. And for these, they have to be in phase as well. So these are, and that is your orbital picture for ethylene.